All right, going to go into some new concepts here, intermolecular forces, and this is really just going to be some memorizing. So we're going to look at two kinds of forces, and it's the forces that hold together nonmetals, so things that really don't make sense that they would be held together. So like water, um, what's holding hydrogen and oxygen together, and so what's holding things together in gases, in liquids, etc. So intermolecular forces and then intramolecular forces. And the ridiculous thing is that they have a name that is so similar, and so we need to be able to understand sort of the differences. So intermolecular forces is what we'll spend most of the time with, and these are actually very weak forces. But we do need to talk about the real quickly intra. So see the difference is INTRA. An intramolecular force is something that holds the atoms making up a molecule. So these are actually bonds. This includes your ionic, your covalent, and your metallic bonds. Now, the difference is that these intramolecular forces, right there, so it's the INTRA. These are actually inside of the molecule, and so they're actually connecting things inside of the molecule, and so intra is actually inside, and so that might be a good thing to write down. And anything inside is going to be much, 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 much stronger. So take a look at this picture. You've got these structures here, these benzene rings. Well, that connection between H and C, or that connection between C and C, that is a covalent bond, and it's really, really, really strong. But there's something that actually is going to attract two of these to each other, like in a liquid. And what is that force? And so it's the difference is the bond inside? Is it connecting a couple of atoms, or is it between molecules? And so the connection in water, which looks like this, that's the intra. Like that is a bond. But then what happens if I've got like 100 waters and they're all stuck together, or 1 billion waters and they're all stuck together in a bottle of water? Well, what's holding them together in their liquid phase? So what's actually holding the molecules together? So the difference is B, intermolecular forces. We're going to be looking at the bonds that exist between molecules. So the key word here is that we're holding molecules together, or we're holding atoms together. You hold atoms together with bonds, you hold molecules together with these intermolecular forces. And so there are 3 of them. You do need to memorize them. They're going to be on the test. London dispersion forces, dipole forces, and H bonds. All right, so there are 3 of them, and you're going to need to know what they are. Now, there are some tricks to learning these, but once you memorize them, then you'll be fine on the test because they're not really that hard. Okay. If you got a big molecule, it's going to have more forces in it than a small one. So that's something that if you have a huge molecule, it's just going to have more forces. If you got a long molecule, something that's stretched out, it's also going to have more forces. And then here we go, number 3. The stronger the intermolecular forces are, you get higher boiling points, you get higher melting points, and you want to write down that if you have strong intermolecular forces, you have higher everything. So you have higher points whether that's a melting point, a boiling point, a freezing point, like everything is going to be higher on these so melting points, boiling points, viscosity, everything is higher. And so maybe we don't say higher points, we just say everything is higher. So if they're asking you for the thing that has the most fill in the blank, then these things with more forces just have higher values. They normally ask about boiling or melting points, though. Okay, that probably doesn't make a ton of sense yet, but it will in a minute. So here we go. Types of intermolecular forces. So the first type is the London forces, and these are the weakest. How do you tell if you have London forces? Well, they are going to be found in all molecules. But you may not remember that molecule is a word that we reserve for non-metals. So if your compound doesn't have metals, then it does have dispersion forces. Simple as that. And these are going to increase. So like this is for Ti. These are going to increase with more molar mass. So like if you have a Ti, just look up how much they weigh on the periodic table. Okay. Don't worry about this a lot, but they produce a very slight plus and a very slight minus, which is how they can magically attract. Don't worry about that. But you do need to know London dispersion force is the weakest. Number 2, dipole forces. These are going to be the ones that are kind of in the middle in terms of strength. And they are going to be found in polar, okay, there's that word again, polar molecules. How do you find out if something's polar? You got to be able to draw the dot structure. And so there we go. We're coming full circle again. Dot structures again. If it's polar, it has dipole. So you can even look at the name. Dipole, right? Like sounds like polar. They're talking about the poles. So if you got a polar molecule, it's going to have dipole forces. Again, this is reserved for things that are non-metals, right? So like if it has NaCl, that's a metal. So it doesn't have any of this stuff, right? But if you have something like CH4, methane, well, it does. So things that have metals don't have any of these. These are strictly reserved for things that are not metals. And the last one here, I guess I cut it off. It must be on the next slide. Let's go look real quick. There it is, hydrogen bonds. Don't know why I did that. Probably the picture got too big. Okay, the umbrella term van der Waals forces is going to include both of the ones that I just talked about. So if they say van der Waals forces, they are using both dipole and London dispersion. Don't worry a lot about van der Waals. Okay, but let's look at this picture. Here's the difference. We're talking about this attraction right here. What the heck is that? That is attracting water molecules to each other. So I don't care about this. That's intra. I care about this, inter. So when we talk about things like boiling point, we're talking about disrupting this force right here that's holding them together. So let's go to the last one. The hydrogen bond. This is a total misnomer because it's not really a bond. We're really talking about the attraction between the hydrogen in one compound and then the oxygen, chlorine, fluorine, or something in another. Okay, so hydrogen bonds are the strongest of these three, not the strongest overall, the strongest of these three. Okay, so when do you get a hydrogen bond? Well, in the molecule, you have to have a hydrogen directly bonded to one of three very, very, very specific elements. So you have nitrogen, oxygen, or fluorine. N, O, or F. Now, if you have multiple hydrogen bonds, you get a little bit more force, but don't worry a lot about that. And so this is interesting. This explains why ice is less dense than water. So like ice cubes float, right? Like that's kind of strange because most solids sink in their liquid form, but ice doesn't. So what happens? Well, here is what happens with your water molecules. So these are water molecules, and they all are attracted to each other because they have hydrogen bonds. They attract, and what happens is they form a pocket of air in the middle, and that pocket of air is going to create a lower density for ice. It's about 10% less than the liquid, and that's because it expands and has the air in there. For more trivia knowledge to win lots of money in the future on a trivia game, the hydrogen bonds are why all of your snowflakes have six sides. Like if you look at a snowflake, it has six sides, and so that's also part of that hydrogen bond. But this ability for ice to float is like really big deal biologically, because like if ice doesn't float and you have like a pond and here's your pond, well, ice floats. So what happens in the winter is it forms a layer of ice on top, and it allows the aquatic life to go down here and just kind of hang out, and they're fine. It actually insulates the water. The fish do great. But let's think about what happens if ice acts like all other solids pretty much. We go back to our pond. So here's our pond again. And so let's say that ice sinks in water. Well, then the ice would start at the bottom. And as the winter progressed, there'd be no insulation. And so then, like, here's your fish, right? And he's like hanging out there. Well, you would just have the ice would continue to grow from the bottom until your entire pond was just a solid block of ice, and you would never have any aquatic life survive the winter. So you'd have no aquatic life anywhere where it got below freezing. And so it's a pretty important biological thing for something like a fish living in a pond. So kind of an interesting thing. Not going to be on test, not going to help you there, but just a little side note. So, okay. Which has a higher boiling point, O2 or N2? Explain your answer. Okay. We got three forces. We check for each force, and then we compare. So we got an O2, and that O2 is going to look like that if you draw the dot structure. So I'm going to cheat a little bit and already draw it out for you. And then you have the N2. Also going to cheat. You can draw your dot structure if you want. Okay, we check for each force. Okay, so what forces is oxygen going to have? Okay, it's made of nonmetals, so it gets dispersion. Dispersion's a yes. That's not polar, so it does not get dipole. There are no hydrogens, so it cannot have hydrogen bonds, so it only has dispersion. So this is dispersion only. Check nitrogen. What does it have? Well, nitrogen's a nonmetal, no metal, so it has dispersion. Not polar, because it's identical, and it doesn't have hydrogens, so it's also dispersion only. So what the heck? We have a tie. So this is a tie. That super stinks. Now I don't know what to do. Well, I do know what to do. There's a tiebreaker. So how